So today we're starting our latest plenary session, Plenary 10, which is Probes of Cosmology, and our first speaker is Weili Penn. We will have a recording for the session, but we are lucky to have Weili live for questions afterwards, and he will be talking about FRBs, coherent probes of space-time.
Yes. Well, welcome everyone. My pleasure to give the first talk, which is still daylight here for the next couple of minutes. I can sit on my patio. And I wanted to give some of the aspects that I find very exciting for FRBs that actually I feel also a underexplored application that I encourage people to think more about and to use more on data. So let me start. The basic properties that I want to use is their coherence. Coherence means that they form an interference pattern under multipath propagation, and I'll talk more about what that means or how that works. This enables a new handle on some old concepts, for example, gravitational lensing. And I'm going to talk a little bit about how this impacts attempts to do gravitational microlensing and gravitational macrolensing. And the more mature lensing application is plasma lensing, which has already been observed. I mentioned that just very briefly. So that opens up the window to use FRBs to probe the universe, what the universe is made out of, perhaps the nature of general relativity or whatever other theory might replace that. And yet another application of this coherence is that we can use these lenses, be they gravitational or plasma lenses, to learn about FRBs. So it's a two-way street. And you might wonder if that's not a circular problem, but we'll get to that. Let me just start off with just the concept of coherence, which is a very uncommon phenomenon in daily life on Earth or on the sky. So very few objects exhibit what I would call diffractive, what people call diffractive scintillation. By diffractive scintillation, what we mean is that the light takes multiple paths towards us and that these paths form an interference pattern. One thing we do see is, for example, twinkling of stars. So atmospheric scintillation can make stars appear to twinkle. And the twinkling is a bit chromatic. It's much more dramatic for pulsars and fast radio bursts that are known to strongly modulate on very narrow frequency intervals and on modestly short timescales of seconds to minutes. So this means that these are the two objects for which you actually can think of them as having a double or multi-slit experiment along the multiple propagating paths. And this has already been observed. And I know last week we had discussions about whether this would happen or not. And I just want to encourage people to look at data and to, just quantify how much it does happen, or if it doesn't, how much it does not. And I'm going to make the general advertising that the plasma lensing is a proof of existence of the compactness and coherence of fast radio burst sources that implies that gravitational microlensing or general gravitational lensing is likely observable. Why didn't it change page? Here we go. So I'm just going to summarize a few known results. One is a relatively old one that's from 2015. That's in this field. This is eternity, one of the first papers in the field, it seems, that FRB110523 is a scattered FRB that was detected at GBT by Xian and analyzed by Kyo. That shows scintillation of the scattering tail, and why that's not, I'm going to explain why that's non-trivial in the next slide. More recently, FRB 2011-24A showed a measurement of a scintillation time scale that was just posted recently by Main et al. And this suddenly allows us to analyze FRBs the way that some of us have been analyzing pulsars and using pulsars to analyze the space-time between us and them. I'm going to mention some examples for the crab that is giving us direct evidence for very high Lorentz factor of the emission region with a very narrow spread of Lorentz factors. So the coherence of the emission has been one of the open mysteries. And while I think it is fairly apparent that a high Lorentz factor makes a lot of the problems much easier, there have been two big challenges to it. One is, why would you have a high Lorentz factor? And then even if you did, how can you get a narrow banded observed features, which are common in FRBs, unless the spread of Lorentz factors is very small, which seems contrived, unless of course it's been measured. So that's why I think these measurements are a big hint and a big lever arm to try to understand mechanisms. So these high Lorentz factors allow you to use, I'm just going to float some words around. Maxime has a beautiful paper on the free electron laser mechanism. A while back, 1971, what's that, 50 years ago, Sterling Colgate already was talking about the gamma squared mirroring effect that may lead to coherent emission. So that's not a very new idea. And that these all may have implications for FRBs, and mostly these are very accessible studies. This may just be a matter of looking at data that already exists. Okay. Now I'm going to speculate a bit about other types of measurements that uses the nature of the coherence of the emissions. If source is really a point source, then under gravitational microlensing, you see two images. So there are two paths between you and the source. And these two paths form an interference pattern. So when you look at different frequencies, and I don't know whether Rafiei gave a talk on that, it allows you to instantaneously measure the mass of a lens, be it a star, planet, dark matter, or something else. There's also a very amusing effect based on imaginary images. So these images can be geometrically not insufficient to form a real image, but wave optics again opens up the new phase space. And I'm just going to give you a dangle in this very short talk. It's going to dangle some, but I think are very amusing possibilities out there. And then, of course, if you have macro lensing, I'm going to spend another slide on that later on. That opens up the potential to measure something to nanosecond time delay, propagating over gigaparsecs. So this you have to ask, what could one measure with such precision? It's a very small, fine number, right? So just if you translate this into a strain, it's a very funny form of strain, but you have light moving along two paths for gigaparsecs, interfering at a nanosecond sensitivity. So there's something that you're measuring to a part in 10 to the minus 26. That's some of the best measurements, period. It's a very tricky one. So you might think, oh, can you measure gravitational waves that way? It turns out the transverseness makes it not couple with this funny geometric pattern. But if you had scalar gravitational waves, it would couple. So we had a paper on that some years ago to discuss it. And at the very bottom, I'm just trying to draw a cartoon, and which shows that if you have an emission, sorry, this is from a pulsar paper, but FRBs may or may not be pulsars. That doesn't actually matter for this purpose. If you have multiple paths going through a scattering screen, arriving at Earth and potentially observed at different observing stations, that allows you to measure a large number of things about the lens and about the source. Back to the gravitational macro lensing potential. So with Olaf, we discussed, analyzed the possibilities of what happens if you were to have a strongly lensed FRBs. A lot of ifs, and a lot of these things we'll have to wait until we actually see them. But there are some new ideas that one should think about. So traditionally, I mean, it's not a new idea to use gravitational lensing to measure a distance. You know, you measure, if you measure the size of an angle, the size in the sky, you measure a time delay. You might have all the ingredients you need to measure an absolute distance. And absolute distance is, of course, if your Hubble constants, dark energy, and other derived observables. But of course, over the years, I think to make this very precise, it's always been difficult to understand the lens models well enough, since there's both gravitational redshift, there's the measuring path differences, you need to know the asymmetries between these lenses. It's actually been tricky to make this into a very robust, precise measurement at the 1% level, which is what one wants these days to be interesting. Now, you can already see that, well, in normal gravitational lensing, you're lucky to measure a time delay to a few hours, and the actual time delay might be a few days. So you measure something to, well, let's say 1%. And you say, well, but if my systematics are also 1%, does it matter if I measure things more accurately? The answer is it does matter. If you now measure things to a nanosecond, the time delays, then suddenly it's a different game altogether. So just by adding, 12 more orders of magnitude, 12 more significant digits to your time delay, suddenly you can ask new questions that you just couldn't ask before. So for example, you have 4 time delays, and if the FRB were to repeat, you measure the 4 time delays a second time, let's say a year later. In that year, a lot of things have happened. The universe has expanded. Of course, the expansion change is huge, as measured in nanoseconds. So you just get an instant snapshot of the universe expansion. A much bigger effect is the transverse motion of the lens itself that will change the time delays. But it turns out that transverse motion only is a 2-component vector. So it eats up 2 of the 3 independent time delays that you've measured. So in principle, there is information left to measure something about the universe. And we have a paper that goes into this discussion into more details. And of course, it's not without complications that these macro lenses will inevitably be split into micro lenses, which again will all be observable through these coherent effects. So you will start to measure the mass function. So even if this doesn't work, you'll still measure the mass function of stars in the lensing galaxy. So a lot of things you can learn that it makes lensing of coherent sources a very different game than regular gravitational lenses of a quasar. Again, they're exciting. I can go on for hours about the interesting tools that one has, that one can use to measure, to calculate the wave effects, the imaginary images.
3 minutes remaining. Sorry to interrupt.
Yeah, thank you. That one can use Picard-Lefschetz theory to try to solve these things. That's, for example, when we have microlensing by planets, it turns out planets are of a size where the wave optics actually fully matters and changes what you actually measure. And I'm just going to jump over that. Here I just want to give a paper that Robert Main wrote that demonstrates plasma lensing of the Black Widow pulsar 1957 plus 20 when the plasma wind of a Born-Dwarf companion causes strong lensing of the FRB itself. And some of the features may relate to phenomenology that FRBs exhibit. So you can see here it's measured in the 300 megahertz band. Some FRBs are also measured in that band. And you can see strong magnification of the pulses as a function of time and frequency that changes with time and changes with frequency. You can see a downward marching series of caustics of the lens that are magnified factors of 10 over what you normally see. So this is as a concrete example of a coherent source that undergoes wave optics plasma lensing, from which we can try to understand things in a more controlled environment that may be a handle to learn more about FRBs. So that brings me to the summary of what I'm trying to advertise here. It's mostly advertise some concept of using coherence, is that the wave optics changes the nature of what one can observe. So one should think more ambitiously. So these FRBs, I think, are a game changer. So they're not just yet another blip on the sky of objects that may be far away and localizable. They may be the most precise thing you can measure, period. 10 to minus 26. There are not many things you can measure to that kind of of precision. That they are describable, they're calculable. It requires some of these things require new tools. Some of them you can use existing iconal tools. So it's a good opportunity to apply tools developed in different fields. Quantum mechanics has been a very successful, of course, toolbox on which one can draw that describes how wave packets propagate. And I want to advertise the applications that have been very successful on the Crab pulsar to think whether we could have similar phenomena for FRBs, because many of them are also scattered. And I'm speculating here based on a sample of one for which we have observational evidence that they are also scattered very close to the source itself and not somewhere halfway along the path. But these are questions we can answer in the near future with existing data. It's just a matter of analyzing the right way. If we can find similarly drifting narrowband pulses, maybe we can measure Lorentz factors of the emission. And whether or not the lens, there was debate about that. It's all things I think we can answer from the plasma lensing properties. And I'm just going to end on something I didn't actually get into, that VLBI measurements of FRBs allow us to probe these certainly plasma lensing effects and also microgravitational lensing, if you were to see them, much more precisely and use them in a coherent way. Thank you.
Thanks, Lupi, for
Great. Thank you so much to Wei Li. I'll applaud for the audience. We have some great questions already, so I'm going to start with Jenny Wagner's question. She says, thank you for the inspiring talk. Can you comment a bit more on effects that destroy the coherence between the multiple images and how likely or unlikely it is that they occur?
If I may just answer the two questions, Clancy's as well, because I think they're very similar in nature.
Go for it.
As to how propagation can affect that.
So maybe read out Clancy's question first, because only we can see it, I think. Yeah.
I see. So can you please comment on how slight differences in path through scattering screens might prevent us from identifying multiple images, e.g. from a gravitational lens, since experimentally one would identify multiple images via coherent cross-correlation of subpulses? And I'm just going to reword this question a little bit, that with very short time these days, let's say a micro lens lensing by a star or a planet or something, you get a microsecond time delay, which is short compared to typical FRB pulses or pulsar pulses. And what one sees is an interference pattern. So you see the intensity modulate over a megahertz bandwidth with a microsecond time delay, and you see an oscillation in the intensity. That's what one would expect to see. And one could be concerned that if the two images then pass through yet another lensing screen, which we know they do because these FRBs are known to scintillate and pulses are known to scintillate, you might be concerned that the interference pattern gets destroyed by the second screen. And while that is in principle possible, the current data suggests otherwise, that the plasma lensing seems to maintain full modulation of FRBs and pulsars, therefore indicating that even the scattering is not, even the scattering is multipath as well, and you might worry about it. The current measurements for the one for which has been published show that this is not a problem, that these lenses do not resolve each other, meaning that they effectively pass through the same lensing screen. This, of course, implies that the scattering is happening very close to the FRB itself and not part way. So that's something which we can only answer by more analysis of existing data. So I encourage everyone to think about and look at the data to establish these coherence effects.
Thank you. Thanks, Wei Li. That's great. I think you covered both questions at the same time. I think, yeah, we're just slightly over time, so we'll move on to the next talk. I'm going to thank Wei Li again. Thank you for the excellent talk. Very inspiring and motivating for the things you can do with cosmology with FRBs.
Thank you.
And we move on to our next speaker, who's going to talk to us about one of the things that you could possibly do with FRBs, which is a new measurement of the Hubble constant using fast radio bursts. And that's Robert Lilow, who is speaking to us from the Department of Physics at the Technion. And he's going to be speaking to us live.
I am.
Robert, I'm going to give you a 3-minute warning.
Yes.
Before, yeah.
Thanks a lot. Thanks also for the introduction. Yeah, first of all, let me thank all the organizers again for creating this great conference, and also giving me an opportunity to talk here. I am still very much a novice with regarding to FRB. I actually got hooked onto this topic together with my two collaborators, Stefan and Robert Reischke, by a talk of Amanda just a bit more than a year ago. So, and this is one of the projects that came out of this, which I would like to talk about today, namely measuring the Hubble constant. So I spared you reminding you of all the basic properties of FRBs, giving the audience. Let me just give you a quick reminder on those properties which are relevant for the cosmological applications in general, and this one specifically. So first of all, FRBs are luminous enough to be visible at cosmic distances. They allow us to cover large redshift ranges, large volumes. That is very crucial. And the dispersion measure probes line of sight integrated electron density, and via this gives us access to a lot of different cosmologically interesting properties. So I'm using here kind of standard split of the observed DM to 3 contributions from the host, the large scale structure along the way, and then our Milky Way, where consider the latter one, the Milky Way contribution. We consider one of the calibrated models and subtract this from the observation. It's more tricky, obviously, for the host, as already been discussed at great length during this conference. I mean, you expect the 1/1 plus z redshift dependence overall for this contribution, but apart from that, it's way more uncertain. There can be additional redshift dependence due to host evolution. The host type will certainly affect the contribution. The position in the host affects the amount of electrons they have to pass through. So there's a lot of uncertainty. So in this study, for the time being, we use a very simple approach. Just say we have a mean plus a Gaussian scatter, which we assume to be Milky Way-like. And then, of course, last but definitely not least, they have the large scale structure contribution, which at least for those FRBs from high redshifts is the dominant one, and which is crucial for the cosmological application, because that is one of the reasons why these FRB DM studies have a very high signal to noise compared to many other studies of cosmology like weak lensing or galaxy clustering, at least given the fixed number of observed events. Now, let me focus a bit on this large scale structure contribution. So it is, of course, given by a line of sight integral over the electron distribution on the way and the IGM. And why are this the couple of things that we directly get access to? First of all, I highlight a few is the global fraction of baryons that people have looked into. And of course, the fraction of baryons then specifically in the IGM. The ionization history definitely plays a role in there as well. But then if you want to go beyond the mean, you can also, for example, look at the electron density fluctuations, which I've described here with electron bias VE relative to total matter. So then you can do interesting probes using angular correlation functions, for example, of the DM. We have done some work on this, but it's not what I'm focused today. What I want to focus today is actually probing the expansion history. And this essentially enters via the dependence of the absolute distances on redshift in this line of sight integral. So before I tell you exactly how we do this for FRBs, let me just tell you a bit more in general about tests of the expansion rate of the Hubble rate H, and specifically the recent Hubble tension. So I'm describing here the Hubble rate in the typical form, splitting it into its value today, H0, and the expansion function E, where for this paper we just assumed a standard flat lambda CDM expression depending on the matter and dark energy density parameters. And then whatever way you want to constrain Hubble, whichever probe you want to use, you basically use some type of distance redshift relation, V of Z, which I've just written here as an abstract form. So you always have some dependence on H0 and of course over the inverse expansion function. But then depending on the specific distance measure you're probing, be it a luminosity distance or angular diameter distance or something more effective, you will have some kernel of redshift here, whatever it might be. And then if you are able to probe both distances and redshifts independently, then you have access to the expansion history or H0 specifically. Now, maybe not in FRBs, but most of the times in cosmology, redshifts are actually the easy thing to measure. Distance are a bit more tricky. So you need some kind of physical scale to as an anchor, basically to get an absolute distance estimate of any kind of object you're observing. And broadly speaking, there are two categories considered for these H0 measurements. There are those where this distance anchor is in the early universe. So that comes then into play from the sound horizon, or equivalently speaking, the Baryon acoustic oscillation scale, before, well, imprinted during decoupling of photons. So this is, for example, the scale that is effectively probed by CMB measurements of H0, like by Planck, for example. And on the other side, you have the late universe measurements, where the distance scale comes into a combination of a local distance ladder and then some standardized property like supernovae, standard candles, or gravitational time delays, or other things. So, and then recently it turned out that we have quite a growing tension between these two categories of measurements, which, depending on how exactly you compare them, is of the order of 4 sigma or larger. And that's the so-called Hubble tension. And this could be down to systematics or new physics or both. And any type of new independent measurement will, of course, be really helpful in shedding some light on that. And that's exactly what we want to do with FRBs. In this case, we use the DMZ relation, so the Makar relation, as an effective noisy distance estimate, as a function of redshift, so to speak. So I'm just writing again the expression for this large-scale structure contribution of dark matter, only its mean, so ignoring the spatial fluctuations, and spelling out specific cosmological parameters that we're interested in. So there are a number of things that this quantity, of course, depends on. First of all, we have still, again, the IgM fraction, ionization fractions in here, which for this analysis, given the redshift range that we're covering, considered to be approximately constant, and use these, well, more or less standard values found also from existing tools. Then, of course, even if you are able to nicely constrain those, then you still have a perfect degeneracy between the baryon density parameter omega b and H0 here. So to really probe H0 on its own, and not only its combination, you need some prior information on omega baryon. There are a couple of ways to do this. You can either use the prior on the combination omega b H0 squared, which you can get either from CMB measurements or Big Bang nuclear synthesis. Or if you, for example, look at the gas fraction in clusters, you can also get a prior directly on omega b to break this degeneracy. All valid possibilities, we focus on the first one for this application. Now, of course, this is only the mean contribution, so we have to consider there is some scatter around this mean due to the density fluctuations along the line of sight. And for this, we use the results found by Jaroczynski in 2090 based on the illustrious Heider simulation, where the scatter spans roughly this range, 40 to 180 units for the redshifts we're interested in. And for simplicity, we assume a linear dependence on redshift to interpolate between those values. Now, if we put all of this together with a suitable data set of FRBs with known hosts redshifts, we can constrain H0. And that's exactly what we did. So at the time of publication, there were 9 FRBs with known host redshifts available. These are the ones shown down here, covering a redshift range of up to nearly 0.7, quite good already. And as you can see here, the black line is the modeled expectation. They nicely follow this trend. And the error bars here basically have 3 different components. There is the uncertainty in the Milky Way model. There is the assumed scatter on the host contribution. And there is the scatter in the large-scale structure contribution, all combined. Now, for the analysis, we look at either the full sample of these 9, or we consider this so-called gold subsample of only these 6 red points, where the 3 black ones are neglected because there is larger uncertainty on the host identification. And here's the result. So as I said, for this study, we use a prior on the combination omega b H0 squared. And specifically, in this case, we actually just fix it directly to the best fit value of Planck, given the low number of FRBs we have so far. That's kind of required. And for the host, these are numbers that we're assuming, the order of 100 plus minus 50 units at redshift 0. Then these are the results what you get as PDFs as a function of H0. All the colored lines are the results for the individual FRBs, where generally speaking, you can see that the more nearby FRBs have a broader distribution. They have less constraining power just because they are more dominated by Milky Way and host uncertainties. So that we get most of the constraining power from the high redshift FRBs. So the combined line that we get then for all of them is this thick black line, and the dotted one for only the gold sample. You can already see here, because the ones that we exclude from the gold sample are mostly from low redshifts, that's why the difference is rather marginal between the two results. Overall, you get these results, 62, 63, plus minus 9 or 10, so it's sort of 16% error in this case. And for comparison, what I'm showing here in blue and green, respectively, are results on the one side from Planck, from CMB, so that's basically the main early universe result we have. And then one of the most prominent late-time results by SHOES, which is a combination of local distance ladder, Cepheids, and supernovae. And basically, these are the two results with like this more than 4 sigma tension. So if you compare our results with that, you can see on the positive note, we get compatible results. However, given the only 9 points we have so far, we had at the time of publication, the error bars are still very, very large. So it's consistent with both. There's no way to really distinguish at the moment. But hopefully this will change in the, well, let's say near future in the next years. And to study this, we looked at a little forecast. So first of all, what I'm showing here is just to get a feel, a very naive extrapolation. So that's very oversimplified, just extrapolating the error bars, saying they will square with the inverse square root of the number of FRBs available, just to get a feel, and that tells you that in principle, the potential is there to reach down to few % precision with a couple of 100 FRBs. Now, of course, if you go down to these precisions, you really have to worry about all the potential biases that are in there. Can come from different sources, but especially the host contribution. Because, for example, if we vary the mean value that we assume for the host, that directly affects, even though in a weaker fashion, but still directly affects the inferred Hubble value. So this is something we have to worry about. But luckily, as soon as we have higher statistics in FRBs with redshifts, we can also relax some of these assumptions to take these uncertainties more appropriately into account. So that's what we, for example, checked in this proper forecast, where we generated 500 mock FRBs following roughly the current redshift distribution of observed FRBs. And to account for the fact that we might not know this mean host contribution very well, we check what happens if, in this case, with 500 FRBs, we leave it as one of the 3 parameters to fit. In this case, it's not completely degenerate because it has a different redshift dependence, allowing us to break that degeneracy. In addition, we leave the meta density parameter omega m3, and instead of fixing this omega b h0 squared combination to a specific value, we only assume a wider prior given by Big Bang nuclear synthesis. And this corner plot here on the right shows our result. So you can see these are results for Hubble, omega m, and the mean host contribution. And as you can see, even though we introduced these 2 additional 3 parameters, given the 500 FRBs, we still get really good results on H0. So this is of the order of, what is it, 3% approximately. And also we actually recover the result that we put into the mocks. So that looks very promising. And with that, I already would like to come to the end and summarize. So as you know, the dispersion measure of FRBs probes the electron distribution, which gives us great access to different cosmological properties. And you can look both at the mean, which I focus on today, but also the correlations of the DM of FRBs to probe cosmology. And they're especially powerful because they have a very high signal to noise compared to many other cosmological observations, and allow us to access very large volumes. So with the 9 FRBs that we had available for this analysis, the constraints are still rather weak, at the order of 62 plus minus 9 kilometers per second per megaparsec, but they are compatible with known values. Of course, in the near future, hopefully we have a few 100 FRBs with host identifications. Given that, much more high precision and independent constraints and not should be possible. But of course, that's not the only thing we can do. As soon as we have an increased number of FRBs, can do much more. Just as a little teaser, I just mentioned 2 other projects we looked into, where we showed that with a few thousand FRBs, But even without having any host identification for those, you already have a good handle on constraining, for example, prime mononomial insanity or the equivalence principle. So I'm happy to discuss any of these topics, of course. And with that, I'm done. Thanks a lot.
Great, that's perfect timing. Big thank you to Robert. Okay, we have a bunch of questions. I'm going to do my best to see if we can get through most of them. The first two come from Brian Gainsler, who's asking, what do you assume for the Milky Way halo, the DM of which is still quite uncertain as per Amanda Cook's talk earlier today, and how much does this affect your results?
Right, so we use one of the available models. I have to say, I forgot, what is it, NE 2001, I just checked, model by Cordes and Lazio from 2002. So we just assume this model, given its values for the, and subtract its value and add its the uncertainty in the model to our overall error budget. So that's what we do for this analysis.
Okay, so Clancy James asks, do you account for selection effects against higher DM FRBs from surveys? McCart et al. Did not, but they discussed this. If not, probably a low value of H0 is expected. Even worse, this effect depends on the FRB luminosity function. If all FRBs are incredibly bright, you overcome this effect for a wide range of redshifts. But if there are many more dim ones, you are very downward biased in dispersion measure and hence H0. And then while we're on the topic, did you also fit for the host DM means and scatter? And if so, how?
Right. So no, that's an excellent point. So for this analysis here, no, we didn't take selection effects on the M into account. But I agree that in principle, given those selection effects, that might lead to the shift towards lower values of H0. Of course, to be fair, given the error bars at the moment, it's hard to say if it's not significant yet. What we checked is that, like, for all of these, the signal to noise, especially for the high Z one, if I remember correctly, is quite decent. So we hope that they are less affected by excluding high DM FRBs. But I agree that it's something that needs to be taken into account as well, especially as soon as we have more statistics. So either taking the selection effect into account or trying to consider subsamples with minimal bias. What was the second part again? Could you remind me?
Sure. The second part is, did you fit for host DM means
right.
and scatter? And if so, how?
Right. So yeah, as I said, for this analysis here, we just fixed the host, because there is just, if we would also leave the host as a free parameter with just 9 FRBs, there's basically no constraining power left. So for the forecast, we checked what happens if we leave this mean contribution as a free parameter. And that's what I said. So in this simple forecast, that still gives us like 3% errors on H. Of course, there's much more that should be taken into account at that stage, which we didn't do yet. The scatter for all of these assumptions is assumed to be fixed. So it's given by, as I said, the result from illustrative simulation. We take into account its H0 dependence during the likelihood analysis. But beyond that, we don't. Sorry, that was the large scale structure scatter. The scatter for the hosts, no, we just use 50 as a guess throughout this analysis for the time being.
So I think there are a lot of questions that you're going to eventually have to take onto Slack, but I'm just going to ask one more because it overlaps with my question. So it's from Stefan Heimersheim, but I'm going to make it more brief, which is basically, what other cosmological priors did you need to put in? So he's asking if you needed to require flatness, and if not, then would using other example Planck, weak lensing, etc., omega matter constraints improve your H0 measurement? But did you, what prior did you put in for,
so for this
omega K and I guess dark energy?
So for this analysis, we assumed it's flat, so omega K was 0. For the actual analysis, we fixed all of those to Planck. For the forecast, we left omega M free, but assumed that omega lambda is just 1 minus omega M. So that's what we did for this. Principle, of course, you could relax any of those assumptions as soon as you have enough statistics, become more model independent, and then just introduce some other priors either on these parameters. You probably would also have to consider priors on things like the IgM fraction, and you could also, of course, consider more interesting hosts DM models, which you could try to constrain at the same time. So hopefully maybe also as soon as we have enough statistics, learn some more about the host properties as well.
Okay, thank you. So there are a couple more questions in the Q&A. You're welcome to type an answer directly or take the conversation to Slack or to GatherTown in one of the breaks. Thank you very much, Robert. That was great. Thank you.
Thanks.
So our next talk, we have Xin Wu from Nanjing University talking to us about an 8.8% determination of the Hubble constant from FRBs. So we're staying on this topic. We might actually get to some of the other questions. And here we have a recording, but if any of the collaborators are present, you're welcome to address questions when we get to them.
Hello, everyone. I'm Xin Wu, a PhD student from Nanjing University in China. It's a great honor to introduce my recent work here. The topic of my report is 8% determination of the Hubble constant from localized fast radio burst. And here are my collaborators. Now we all know that the universe is expanding, and one of the most important questions in cosmology is measuring the expanding rate of the universe, which is the Hubble constant. People have used the different methods to measure Hubble constant, measuring the luminosity distance of nearby stars and establishing a cosmological ladder is a traditional measurement method. In this plot, blue stars correspond to the measurement of Hubble constant in the local universe with calibration based on CFAS. Another remarkable method is to use the power spectrum of cosmic microwave background to measure Hubble constant. In this plot, the red dots refer to derived values of Hubble constant from the CMB, assuming a lambda CDM model. However, with the improvement of observation accuracy, the measurement deviation under the two different methods is larger and larger. And the difference is up to 4.4 sigma now, which is also called the Hubble tension. Now, measuring Hubble constant with gravitational wave has become a more reliable method. The green courses are direct measurement of Hubble constant with standard series. Now, one urgently needs new distance indicators to test the Hubble tension. As a new cosmological probe, FRB can be used to measure Hubble constant. Firstly, I will give a brief overview of FRB here. FRB is a bright radio transient source with cosmological origin. FRB is very special that has very short duration. And the dispersion measure value of FRB is very huge, that far exceeding the DM value contributed by the Milky Way. It has a very high brightness temperature, which means that its radiation mechanism should be coherent. And the current research shows that some repeating FRBs have long-term periodicity, including FRB 1809-16 and the FRB 1211-02. With the search of CHIME with large field of view, more than 600 FRBs have been found. This figure shows the position of all the FRBs in the sky maps. For FRB, a very important observation is the dispersion measure value, which is defined as integrated Coulomb density of free electrons between observer and the source, as this formula shows. The most significant factor affecting DM is the value and the distribution of electron number density. As shown in this figure, when a FRB reaches to the Earth, it will pass through the host galaxy, intergalactic medium, and the Milky Way. Obviously, the observed DM mainly comes from the contribution of these three parts. Next, I will introduce how to determine the DM values of these three parts. The first is the contribution of Milky Way, which divided into two parts. the interstellar medium and the halo. The contribution of interstellar medium can be divided according to the galactic pulsar model, NE 2001 model, and the YMW16 model. While the contribution of the halo is between 50 and 80. Here we assume 50. For the contribution of the intergalactic medium, so-called IGM, the average value of DMIGM can be expressed as the relationship with this with redshift. That is in this question. Here we express the Hubble constant separately, and the other can be given by other observations. We can use this relationship to measure Hubble constant with FRB. The last and most difficult to handle is a DM contributed by host galaxy, because the properties of host galaxy of FRB are different, and the FRB is located in different positions in the galaxy. There are significant differences in DM host between different FRBs. Actually, I used to measure Hubble parameters with FRB before. In the flat number CDM model, the expression of Hubble parameter is shown by this formula. We know that there is a dependence between the average DMIGM and Hubble parameter. Therefore, as long as we know the redshift and DM value of FRB, we can measure Hubble parameter according to the dependence. Since the number of localized FRBs known at that time was very small, we simulated 500 FRBs using Monte Carlo method, as shown in this left figure. The DM and the redshift of FRB are shown here. The redshift range is assumed 0 to 3. The results are shown in the right figure. The red line here is a theoretical value, and the blue points are Hubble constant, Hubble parameters calculated according to FRBs. We found that the maximum deviation of Hubble parameters from standard nominal CDM model is about 6% at redshift 2.4, and the p-value of case test is 0.23, which confirms the internal consistency of this simulation. This result showed that it is effective to use FRB as a cosmological probe to measure cosmological parameters. That also prompted me to measure the Hubble constant with FRB when the number of localized FRBs are enough. However, a problem that needs further consideration is how to get more accurate DMIGM and DM host. For different FRBs, DM host will be different according to the properties of host galaxy and the location of FRB in the galaxy. Here, we assume that DM host satisfies a log-normal distribution, as shown in the above figure on the right. This is DM host distribution with a redshift of 0.2 in June 2020. As shown, we take this distribution to present the DM host. The other is the distribution of DMIGM. Because the electron number density and the line of sight direction in different FRB propagation paths are different, the DMIGM value between different FRBs vary greatly. In this paper, we consider such a distribution obtained by TNG simulation to describe DMIGM. As shown in the lower right figure, this is a probability distribution of DMIGM at different redshifts given by June 2021 through simulation. For detailed introduction, please refer to Wang-Stokes. Once we have these two distributions, we can give the likelihood function and then calculate Hubble constant through Monte Carlo Markov chain analysis. With the improvement of the observation, more and more FRBs are located now. Here we list 14 localized FRBs. The table on the left shows the FRB name and the redshift. This plot on the right shows the DMIGM value and the redshift after deducting the Milky Way and DM host according to distribution. The blue line corresponds to the DMIGM results from the Tianjin 300 cosmological simulation, and the purple shaded area is a 95% confidence region. The red line shows the model. It can be seen that basically all the observations that are within this range. And then we use the Mcmc analysis. And here we show the results of our measurement of Hubble constant, which are shown in this figure. The black solid line shows the probability density distribution of Hubble constant, while the area between the two green vertical lines show the results at 1 sigma confidence interval, and the blue vertical lines correspond to the Hubble constant derived by GW17 or A17 at 1 sigma confidence interval. The orange and yellow region correspond to the 1 sigma uncertainty range of Hubble constant derived by supernova and CMB respectively. It can be seen from this figure that the accuracy of measurement of Hubble constant is relatively better than the measurement of GW17 or A17. Although it's not as accurate as the measurement of Hubble constant by CMB and supernova, it is mainly due to the insufficient amount of data. From this figure, we can see that the limit result of FRB is closer to the result of CMB. However, the current measurement accuracy cannot completely exclude the result of supernova. Moreover, according to the current development trend of FRB observation, we expect more localized FRBs in the near future. As I said before, FRB observation is in a period of rapid development now. In order to predict the ability of FRB to measure Hubble constant, we use Monte Carlo method to simulate 100 FRBs with a redshift distribution similar to gamma ray burst. The simulated points are blue points in this figure. Next, we adopted Mcmc analysis to measure Hubble constant. Here is the results to constrain Hubble constant. And the error is only 2.6% in 1 sigma confidence region. This error is small, so it is also enhances our confidence in measuring Hubble constant using localized FRBs. If we have enough localized FRBs, we can give a good limit to Hubble constant so as to alleviate
3 minutes remaining.
Okay, thank you. The Hubble tension. Of course, the key point is the number of the localized FRBs, which requires better observation equipment and technology. At present, the telescope we use to locate many, including VIBI, DSA-10, SCAP, VIA. It is believed that with more accurate positioning of this telescope, we can take a breakthrough in the number of localized FRBs. Next is my conclusion. The Hubble constant derived by 14 localized FRBs is 64.67 plus 5.62 and minus 4.66 with 8.7% uncertainty. The Hubble constant derived by 100 simulated FRBs is more accurate, and the uncertainty is 2.6%. FRBs can provide a promising and novel way to measure Hubble constant, which is of great significance to the study of cosmological expansion and alleviate the Hubble tension. More localized FRBs are needed in the for cosmological application in the near future. And thank you for your listening.
That's great. Let's thank Shin. Well, I guess I thank for all of us. I'm not sure if she's available or if any of the collaborators are available for questions. Though there aren't any in the Q&A at the moment, perhaps the H0 discussion that needed to be had is had. Okay, I'll defer any further discussion to Slack given the absence. Oh, is there a someone volunteering? No, okay. So let us move on. And if there are any questions, please do take it to the Slack channel. It'll be very good to thrash out and continue these discussions. Our next talk for today is by Stefan Heimersheim on model-independent constraints of hydrogen reionization with fast radio bursts. And I believe he is speaking live.
Yes, I am.
Fantastic. I'll give you a 3-minute warning.
Thank you.
Only if you need it.
Okay, that's fine. Yeah, I'm Stefan. I'm a PhD student at the University of Cambridge. And together with Nina Sartorio, Anastasia Kvialkov, and Dan Kloimer, we have been looking at hydrogen reionization and how we can constrain it with fast radio bursts. And you might have seen a few forecasts for this over the last year. And what we want to do in particular here is address the biases and assumptions that go into current analysis and show and convince you how we can get over them with model-independent methods, and that we can still get a really good optical depth and reionization constraints with that. So let me start with my kind of cosmologist picture and show you this little picture. In the universe, we have already well studied kind of the early time, the first few 100,000 years, mostly with the CMB. And we've also quite well studied the last few billion years with galaxy surveys and other observations. But there's this part in the middle, the dark ages and the era of reionization, that we know very little about. And you also see this if you look at our cosmological standard model, which has 6 parameters, 5 of which we have constrained very well with the little asterisks for the H0 tension here. But the optical depth of reionization, tau, which is a parameter that mainly describes this area, is very unconstrained. And current probes that we have of reionization include galaxies and quasars that maybe go up to redshift 7 or 8, but we're missing probes that go to higher redshifts than that. And fast radio bursts could provide such a probe because they might come from stellar sources as opposed to, say, AGNs that we need for galaxy quasars. So you could get them at much higher redshifts. And of course, similar to the last 2 talks, what we want to use is the IGM contribution to this dispersion measure. So we want to take the observed values and subtract the Milky Way in the host contribution with a certain error. And then we look at this equation here for the IGM contribution. And I split this up a bit differently than the last 2 talks. So here in this term, you see the kind of background cosmology. So you have the omega B, the baryon abundance, and you also probably the Macquart 2020 paper measuring the missing baryons. And of course, we have the expansion rate here. We can measure H0, as you just saw in the last 2 talks, as well as maybe omega M or the dark energy equation of state. And then the second part of this equation that tells you how many of those baryons are actually ionized. So how many free electrons do we have that can cause dispersion? And this is related to how ionized the universe is. So we know in this little cartoon that shows you the amount of electrons per hydrogen, and that the universe must have been neutral at very high redshifts. And we know by about redshift 5.5 it is ionized, at least hydrogen and the first helium reionization are completed. The second helium reionization at redshift about 3 to 3.5 I'm not looking at today. And then our targets for this hydrogen reionization are first the ionized fraction as a function of redshift, so this xi of z function we would like to constrain, and the optical depth tau, which is basically a number that tells you how many of the photons that come from the CMB are rescattered in the reionized universe. And this is very helpful for CMB analysis. So how do we use this dispersion measure to constrain the ionized history? Well, basically, we can use this formula from earlier, this integral. And if we had a perfect measure of the dispersion measure, we could, as a function of redshift, we could directly read off the ionized fraction from the integral. However, we won't have such a perfect measurement anytime soon. So what you would usually do is parameterize your ionization history for the few parameters and try to use your existing observations to constrain these parameters. So a very popular model, both in CMB analysis and in some FRB papers, is the TAN-H step function model, which has two parameters. So you see here, it has the redshift of reionization and the width of reionization, which allows you to kind of parameterize this ionized reionization history as a function of redshift. And then you can translate this to how the dispersion measure for depending on the redshift looks like. And you can imagine if you have a few observations here, you can constrain these parameters, and from that you can constrain the reionization. An alternative would be to use astrophysical simulations, where you choose some astrophysical parameters, then run a simulation to get the ionized history, and from that again you can get the dm of Z relation, and again constrain this as observations, find constraint on astrophysics, and then on reionization, which also has been done in a recent paper for FRBs. And the problem with all of these methods is you somehow parameterize or simulate your ionization history. And what if reality doesn't correspond to your model? So for example, if you would use this TAN-H step function model and use kind of a realistic synthetic data set of 1,000 FRBs localized, then you would underestimate the optical depth by 10%, and actually quite significantly by a few sigma. And also if you would use better kind of descriptions of this shape, whenever you are not including whatever is the real description, the real shape of the reionization history, which we unfortunately don't know yet, you will always get some bias or some inaccuracy in this constraint. And if we want fast radiables to be the best constraint of reionization in the future, we have to find a way around these problems. And luckily, the CMB community had to deal with a similar problem over the last years. And the most recent method that has been developed there is the so-called flex knot method. So let me explain this briefly. If you remember, we have what we want to constrain is this ionized history, ionized fraction as a function of redshift. And we know it must be 1 at very low redshift and 0 at very high redshift. So what we can do is just put a few points in between here and connect the lines, just interpolate. And then we can choose the positions, these coordinates of those interpolation points or so-called knots as our parameters for our model. Then we can just run an MCMC chain on these parameters, and what we get out are contours like down here. So you get the positions of the parameters, and you can constrain what the ionization history is without having made any assumptions in the beginning. And of course, you might ask now a very good question: how many of these knots, how many of these interpolation points do I need? And if I, of course, am too simple, I just take two points here that I can only fit a linear function. Of course, it's going to work not well at all for any realistic reionization history. If I add a few more interpolation points, I can already get quite a good fit. But then I can add more and more, and you ask yourself, when do I stop adding more knots, or what number should I use? And the good thing is that we don't have to decide this. We can also just treat this number of knots, like the detail of interpolation, as a free parameter of our model and marginalize, i.e. average over it, like we would over any other parameter. And how this works out in practice is that the weight of each of these scenarios of how many knots you use will be the Bayesian evidence. So when you have a model, multiple models that fit the data similarly well, but one of them requires many more parameters or includes, then the evidence of this model will be much lower. So you see this in this plot at the right, where I use the same synthetic data set for a different number of knots, so different model complexity. And you see the evidence, so the weight of each model first goes up as you get better fits, but then it goes steeply down when you add too many parameters, i.e. unneeded parameters. So in theory, you would kind of average over all possible number of knots, but in practice, it's enough if you take the first 10 or so models and you see the evidence will go down. Now then, in order to see what we can do with this, and of course also to test the method, we do generate some mock data, some synthetic data, because unfortunately we don't have high redshift localized fast radial bursts yet. So what we do, we first generate some source redshifts. We just take the star formation history, which seems like a plausible distribution for the sources at the moment. And our target is kind of redshift 5 to 15, which is kind of the redshift range where we expect hydrogen reionization. Although if we use this distribution, most of our FRBs will be at redshifts below 10, kind of lower-ish redshifts. And of course, this could change if you assume different star formation histories, if there are top 3 stars that create higher redshift FRBs. And now the two questions you might ask is, first, can we find these FRBs? Can we observe them? And the FAST telescope is already searching for FRBs and could maybe detect them up to redshift 10. And also Green GPT is searching for high dispersion matter FRBs. So you could get there. The harder question is the localization of those FRBs. So we might need DSA 2000 or SKA to actually localize the FRBs so we can measure the host galaxy redshift, or maybe other telescopes that are upgraded with outriggers to increase their location accuracy. Now, to finish generating the synthetic data set, we do add all the relevant uncertainties. So here on this plot, you see a bit the uncertainty as a function of redshift for the different contributions. And the main one, this blue curve here, is the IgM inhomogeneity, i.e. how when you have an FRB at a certain distance, the amount of matter or electrons between the FRB and us is not always the cosmological average, but the universe might be a bit over or underdense in this part, and this will give you a few % uncertainty on the dispersion measure. Then for the redshift determination, we assume a 10% accurate redshift measurement, which means, of course, this is a redshift error, not a dispersion measure error, but to roughly translate it, this will be slightly less than this cosmological error. So if you can determine the redshift up to 10%, that's good enough, but we shouldn't have a much higher error than that. And the remaining two uncertainties that we take here are the host contribution and the observational error, but both of these tend to be subdominant compared to the cosmology contribution, especially because the host one is suppressed with redshift, and the observational error, of course, depends on how bright the FRB is. If it's too dim, it can actually be dominating. Then here you see in these orange points the data set we finally generate. So the green lines will be kind of the true dispersion measure if you had a homogeneous IgM and no uncertainties, and the yellow ones are the kind of synthetic observations. Now, to show you one of our main results, the reionization history constraint that we get from, in this case, 1,000 simulated FRBs. And this plot shows you, again, this ionized fraction of the function of redshift. And these colored contours show you the kind of posterior constraint on this function. So you see that, especially for the lower redshifts, we get a really good constraint. We could get a really strong constraint on the midpoint of reionization. And it also matches with this dashed line, which is the data we put in. So this is the curve we use to generate the mock data. So that's quite well. We do see that at high redshifts, FRBs can't deliver really good constraints. But there's actually a really nice synergy we can use here. And because the cosmic microwave background is particularly sensitive for very high redshift ionization. And actually, there's an upper limit on the optical depth between redshift 15 and 30, or just above redshift 15 from the CMB, that we can add as a constraint to, if you see, if you compare the two plots, we get a better constraint here. And the reason we can do that is, as opposed to having just a few points in the space, every of our sample is a complete function xi of z. So we can take this function and say integrate it from redshift 15 to 30 to get this number and apply this constraint. So that's a nice thing when you have this function. Another nice thing is, as I mentioned earlier, you could derive, say, the midpoint or maybe the start of reionization where we have, say, 50% ionized, 10% ionized, or something like that. I can just take all these functions, for every function, calculate this redshift, and then look at the distribution of these redshifts. And this constraint is actually also a really strong constraint that we can get from these 1,000 FRBs. Now, finally, I just want to show you some cosmology constraints. So the most interesting, of course, is the optical depth, reionization optical depth. And what we do here is we just marginalize over all those possible histories. So we integrate over all possibilities and just look at what is the optical depth, and also what is the other two parameters we vary are omega b over h, so baryon abundance over h naught, and the omega m, the matter abundance. And the tau constraint is quite independent of these two, so we just look at that for now. And you see, compared to the Planck constraint, which is the dashed black line here, the FRBs, you can get a much better constraint, especially on the low end, because it's much easier to detect kind of a late reionization with FRBs. So you could get quite competitive constraints, even if you have, I'll just say, quote unquote, just 100 FRBs here. And once you get this optical depth constraint, this doesn't just help you to kind of constrain this last parameter of our model, but also it improves other parameters, such as the primordial amplitude AS, which is, if you look at this grade contour, already degenerate in normal analysis with tau. So if you increase tau, you automatically also increase the accuracy of this parameter. And in the future for neutrino masses, this will be also very relevant degeneracy between tau and the neutrino masses. So it will be very helpful for these analyses. So I'll just leave you with my summary and hope I can convince you that FRBs will be a really good constraint of reionization in the future. And importantly, that we have this model independent methods that do work and that we should use if we want to avoid various biases. And yeah, feel free to ask me questions right now, or if you're watching the recording on Slack or via email. And feel free to look at the paper on archive, or if you are interested, the source code for all the analysis is on GitHub here. Thank you.
Thank you very much, Stefan. That was really, really interesting. So there are a couple of questions. To start with, Susumi Inui asks, the degree of inhomogeneity during reionization is an important unknown, depending on the nature of the sources, halo mass, dependence of escape fraction, etc. It's something we'd also like to know in addition to the average reionization history. Could you be more specific about how the associated uncertainties are taken into account when inferring how many FRBs it takes to achieve your goal?
So we currently don't take into account the inhomogeneity of reionization. So the inhomogeneity we take into account is the meta inhomogeneity. Just like this is this IgM scatter that we take into account. We don't take into account, like, say, the bubbles in the reionization. They should be small enough that this is not noticeable on this level. Although if we would have many more fast radio bursts, it might be possible, as you just asked, to constrain, say, the bubble sizes of the bubbles during reionization. Although I think you would need much more than 100 FRBs to get meaningful constraints on that. I'm not sure if I answered all of the question, or if there was another part.
Just about taking into account the uncertainties.
And yeah, so
when
we don't take
how many you need, yeah.
any reionization inhomogeneity into account, but we do take the IgM uncertainty. We take the kind of fitting formula of this error from the Jaroszynski, I think 2019 estimation, the 20% overall square root of redshift as uncertainty on this.
And do you think that this is not one of the questions, just a follow-up from me. Do you think that your estimate of FRBs at that high redshift is plausible?
So basically, we just took the star formation rate here, so we don't have a selection function built in for a certain telescope. And I think the star formation rate seems like a plausible. I mean, we don't know exactly yet what's caused FRBs, so the distribution might be different. And the star formation rate might be different to what we've assumed here, although both seem plausible assumptions for the distribution. So I think that's
just the detectability is the secret one.
Yes, that's a question. There was a paper by Hashimoto et al., I think last year, for SKA looking at the detectability, and they had quite a few of high redshift FRBs they forecasted to be detected. I think it was on the order, I'm not sure, I think hundreds or so at beyond 6 or something.
Actually, yeah, the next question is on this exact topic. So let me just read it in case you have more to say. It's Cristiano Guidorzi, and he says, did you account for the detection efficiency of high redshift FRBs of current upcoming radio facilities? It's key to your analysis, but detecting them will be way more challenging than detecting, very local events.
Yeah, no, so we don't take a selection function for the detection into account. And we don't have the problem that we have with that you mentioned earlier with the H0 ones. No, sorry. We don't have the problem that it is the bias of detecting only nearby ones would bias our thought where the FRB is, because we do assume to have the redshift. But yes, the selection will probably move this distribution of FRBs more towards lower redshifts. But yeah, I think that this would just then we would need slightly more FRBs or slightly more at higher redshifts, but it wouldn't bias the analysis.
Okay, so a good question, follow up on that bias issue. Basically, how important is the localization? So Brian Gainsler asks, can we do anything with a large number of high dispersion measure unlocalized bursts?
Yes, that's a very good question. I think it was also in the Slack earlier. Basically, with this method that I show here, we do need localizations, we do need redshifts. There are some methods that use unlocalized FRBs. So I linked the paper of Benyamini et al. In the Slack, which uses either the just maximum DM. So if you look at this plot here, you could imagine if you measure this maximum dispersion measure, you could also infer tau, although there are some problems such as you can't distinguish various histories. Or you could use the distribution of DMs. So just kind of look at a histogram of the dispersion measures and also infer reionization from that. Although for this one, you would need to know rather accurately, the source distribution of over redshift of FRBs. So those are two methods. And there was another paper 2020, I think Dai and Xia, that looked at large-scale structure of FRBs information, where you also don't need accurate redshifts to constrain reionization.
Great, that's very interesting. Thank you very much. So I think let me thank you again. And any further questions, please, people do take them to Slack and to any Gather Town or coffee discussions.
Thank you.
Great talk. Thank you so much. Our next speaker is live from Tokyo, talking about constraining the cosmic baryon distribution with spectroscopic foreground mapping of FRBs. And the speaker is Khee-Gan Lee.
Can you hear me okay?
Yep.
Okay.
I'll give you a 3-minute warning, yeah? If you're not on your summary slide.
Okay. Okay, so thanks a lot for the organizers for giving me the opportunity to give a talk. I'm not usually working in this field, so quick introduction. I'm KG from assistant professor at Kavli IPMU near Tokyo. And first of all, I want to give credits. A lot of the work that we're working on right now are being done by a couple of postdocs at IPMU, Metin and Ilya, and also by a student called Yuzin, as well as collaborators in UCSC and Católica in Chile. And a lot of the stuff I'm going to be talking about is basically collaboration from Craft and F4. So basically they find FRBs and localize them by F4 collaboration localizes them, and then we follow up in Foreground. So the background is this, basically this issue of the cosmic baryon distribution that we've already heard a few times in this talk. And so this is the McCart relationship that shows you the cosmic dispersion measure, i.e. the free electrons in the universe as a function of redshift. And of course, this was a beautiful paper that demonstrated that the cosmic baryons are indeed out there. So the missing baryon problem has been solved. But it did not answer the questions for the relative distribution of baryons. So basically, it's figured out that we've dropped our keys somewhere in the living room, but exactly where the keys are in the living room, we still haven't figured out. Of course, the solid line here is the average DM cosmic relationship, where there's a large distribution of possible DM values at fixed redshift, depending on whether the sightline, for example, passes through overdense regions or individual galaxy halos near the sightline, or conversely, you could have cases where the sightline is passing through underdensities and no galaxies. So even for a localized FRB, you've got this large spread of this DM cosmic. So if you're trying to figure out, for example, how much of the fraction of cosmic baryons are in the diffuse IgM, that's going to be a limiting factor. So the basic goal of what I'm going to be talking about is to constrain the relative partition of cosmic baryons, i.e. between the intergalactic medium and individual galaxy halos. So the kind of framework that I'm going to be talking about is, again, is something that's been shown in some form or another already a few times today. But one thing that I think is going to be unique in this talk is that most other talks will lump together the intergalactic components and typically being called DM IgM. But I would like to split out a further term, which is DM halo, which is caused by individual halos that by being intersected by the sightline. So when I talk about the diffuse IgM, I'm going to be talking about the relatively low density IgM that typically have overdensities of less than 10, whereas DM halo is going to be coming from individual galaxy circumgalactic media. So the basic premise is that we want to have for any given localized FRB sightline, we want to have a census of the galaxies in the foreground, as well as map out the full diffuse cosmic web by other methods. So basically, in this famous equation where you calculate the DM contribution from the from the extragalactic component. Basically, typically, there's going to be an integral here where typically you're forced to average over all possible sightlines in the universe. And in our case, we would like to separate out this factor, or rather this integrand for individual sightlines. So this idea is not new. So Sima et al. 2020 studied FRB190608, which was a FRB that fortuitously intersected, happened to be in the SDSS spectrum. So they did some analysis of what are the possible contributions of the DM halo and DM IGM. So I'm going to be talking about the same idea, except that now we would like to extend this to higher redshifts and much larger samples, and use that to directly constrain the partition of cosmic baryons. So the goal is, I've already described my goal. So the method in this paper is to use a simulation. So we use the Henry Case 2015 semi-elliptic catalogs that were derived from the Millennium simulation. So I think literally everyone has seen this specific picture, which is indeed of the Millennium simulation. And so Henry Case et al. Have released a large number of catalogs where there are galaxy positions and mock positions and synthetic photometry they can directly use to simulate. All framework that we adopt. So we adopt a model where the DM-IGM arises directly from traces directly the fluctuations of the large-scale structure, modulated by some fraction of cosmic baryons that happen to be in the IGM. DM halo is described for each galaxy by a modified NFW function, where the CGM extends to some factor Rmax in units of the virial radius of the halo, and also by the fraction of halo baryons relative to the total mass of the galaxy. And then we also assume that there's an unknown DM host that is fixed for all FRBs. So when we sum this together for each sightline, we also introduce an error of around 15 parsecs per cc to account for uncertainties in the Milky Way subtraction. So as I said, we calculate for mock sightlines within this light cone catalog, we calculate the DM that would be measured from the FRB at that position. We also list down the galaxies that are within 10 arc minutes of the FRB sightline, and we introduce an uncertainty of 0.3 dex in the halo mass within this intervening galaxy catalog. And in conjunction with that, we also save large-scale galaxy catalogs of thousands of galaxies that are with several square degrees around the foreground field, and we define several samples to cover various redshifts that the FRB might be at. So I'm going to introduce the idea called matter density reconstructions. So the basic premise is very simple. So given an observed sample of galaxy redshifts, what is the most likely matter density field that is consistent with this density field? So I'm going to be working with a method called Argo, which is a Bayesian density reconstruction method written by Metin, an IPMU postdoc. And basically, it's a Hamiltonian Monte Carlo sampler that samples from the posterior distribution of the possible density field. So this illustration demonstrates that, where given a sample of observed galaxy redshifts that lie on top of the true density field, it does a good job of recovering the large-scale structure in the volume. So this is a further illustration of the technique. So Argo is a Hamiltonian MC method, and it samples from the posterior. So it literally generates thousands of density fields, which is illustrated here. So the color scale here show the density fields within the simulation volume. The dots show the galaxy redshifts from which these density fields were estimated. So basically each of the line of sight densities, and the green here shows a kind of hypothetical FRB. So basically the point is that we can trace out the fluctuations along the line of sight to the FRB, and the different Monte Carlo samples allow us to even estimate the uncertainty in this estimate. So what is the effect of this density reconstruction on your IGM studies potentially? So this again an example of a McCord relationship, and again the gray region is the cosmic variance uncertainty, where you at a fixed redshift you don't know exactly how much the DM IGM is, and the red points here are the DM IGM from random sightlines that have been extracted from the simulation. The error bars here indicate the uncertainty from the Argo reconstruction. So after applying Argo to the set of foreground galaxy redshifts, we can recover the true DM IGM to within the error bars. It typically about beating cosmic variance by a factor of 3 at low redshifts. At the high redshifts here, we've defined the galaxy samples that we defined were a bit sparse, so it didn't function well. But we are still trying to improve on this method. So we're interested in constraining the cosmic baryon distribution, as I mentioned earlier, described by these 4 free parameters. So basically, we are building a parameter analysis framework. Framework, where given the DM observed by the FRB measurement, we want to find the best combination of these models that fit the observed DM. So we are going to be sampling over FIGM, which is simply scales up the DM IGM relative to the underlying Mayer density relationship, and also the couple of halo parameters that describe the CGM of the intervening halos, and then also DM host. And this effort is being led by Ilya, another IPMU postdoc. So for now, we are working with Fischer Forecast, where this sum is over the ensemble of sightlines that are from the simulation. So basically, the assumptions here are that we adopt the uncertainty from the Argo line of sight reconstructions, and also in terms of modeling the intervening galaxies, that we also assume that we only know the halo masses to within 0.3 dex. So on the right here, I'm showing the Fischer forecast for our 4 free parameters, given a sample of 30 FRBs at redshifts of between 0.1 and 0.5. So you can see that we get around 10% measure estimation of the diffuse baryon fraction, as well as around 20% measurements of the parameters that govern the CGM. And this is, as I said, assuming 30 localized FRBs where we have this foreground data. So just to give you a sense for how much the foreground information buys us, we did the same Fischer forecast where we assume that we have no information about the foreground except for the redshift of the FRB. And you can see that like the constraints are all a factor of 3 worse for the same number of FRBs. And if you ask what is the equivalent improvement in the statistical power of each FRB, we did a forecast for 90 FRBs, and you can see that even with 90 FRBs, the constraints in the absence of foreground data are still not quite at the same level as the 30 FRBs with the foreground data. So the statistical power of each FRB is improved by at least 3. We are still building the MCMC framework to do this, but there is a manifestation of this. To zero the MCMC constraints are the same as the IGM, are roughly the same as the Fischer forecast, but we are struggling a little bit with the fact that the errors are non-Gaussian. So this is work in progress. So we are currently running a spectroscopic survey on the Australian Anglo-Australian telescope in Siding Spring, Australia, on the A omega spectrograph to target FRB fields that have been localized by Craft, F4, and other projects. And we've already been observing since the past fall. So the basic idea for FlimFlam is that we are targeting individual roughly 3 square degree fields on each localized FRB. We try to adopt a simple magnitude limited selection to enable a clean calculation of the selection functions. And to give you a sense for kind of the numbers of galaxies that we have to target for our fiducial redshift 0.3 FRB, we're going to do a R magnitude less than 19.8 selection, which for those of you who are galaxy people, we recognize as roughly the same magnitude cut as gamma. And we're targeting the same field in front of each FRB to gather about 1,500 to 2,000 galaxies, equivalent to about 1 night of AAT observations for each field at this redshift. So the plot below shows you some preliminary data in the field of FRB 180924 at redshift 0.03, redshift 0.3. Reductions done by my student Yuxin Huang. And there are also coordinated observations by using KEC and other facilities to target intervening galaxies within a few arc minutes of each FRB fields. That's being led by Sunil Simha and Nicholas Tejos and Xavier Prochaska. There's a lot of work that remains to be done. So for example, we've heard in this conference that there's possibly distributions of DM hosts, not just a single value. We can either incorporate individual DM host estimates into each sightline reconstruction, or we can adopt a finite distribution if required. There's much work to be done for improving Argo. We think we can do better than the 3 times cosmic variance. The halo mass is a major factor. So something like 0.3 dex uncertainty in the halo mass is actually a factor of 2. And like an error factor of 2 in the halo mass of a massive galaxy that's near the sightline can lead to large errors in the DM. So we're thinking about using ML methods to improve the halo mass estimation. One interesting idea is to invert our method, where instead of having the IGM, CGM parameters as the free parameter, we take the FRB redshift as the free parameter. So if you have a particularly interesting FRB where you're not quite sure about the localization, you can map out the foreground to nail down the DM, IGM, and DM halo contributions, which would either let you constrain the FRB redshift or the DM host contribution. And then there's a few more possible projects where we might want to model things more accurately using hydrodynamical simulations. We could also leverage the foreground information for rotation measure studies of cosmic magnetism. And analysis could also set free the cosmological parameters, which so far we have been fixing to plan cosmology. But in principle, with a large enough sample set, we could feel confident enough to set free the cosmological parameters as well. So I think I will just leave out my summary and take questions.
That's great. Thank you so much. So I see that we have the first question. What is the maximum redshift up to which such a method of identifying all intervening halos is feasible?
The answer depends on how big of a telescope and how much time you're willing to spend on it, and whether you have a multi-object spectrograph. So there's a couple of 8 meter class multi-object spectrographs that's going to come online on Subaru and VLT in the next couple of years. And this, in principle, should get us up to redshift 1 with 1 night of observations. We have some crazy ideas that if eventually we find, say, redshift 3.5 FRBs, we might be able to get the entire foreground field with several nights of Subaru, and that will get us to the epoch of helium reionization. But typically, currently we are limited to around redshift 0.5 with the AAT, which is a 4-meter facility. But with 8-meter class facilities coming online, we can push quite easily to 1 and potentially.
Okay, very good. Any other questions? Otherwise, I'll ask you mine. Let me just quickly see if there's any in the chat. No, okay. So I get to ask you. So on your slide before, there were sort of 2 things I wanted to follow up on. The one was, was the question of using machine learning inference to improve the halo mass estimation. I'm wondering if you can expand on what you have in mind there, sort of which machine learning techniques or how you think it will be useful.
Yeah, I mean, this is very much entirely hand waving at the moment. And but basically right now, when you want to estimate halo mass for a galaxy, you basically estimate its stellar mass either from photometry, like basically from the spectrophotometry. You measure its stellar mass and then you convert it to the halo mass using stellar mass halo mass relationship. Basically, that leaves out a lot of information that in principle, for example, there could be correlations with the luminosity of the galaxy, with the morphology of the galaxy, etc. And right now, there is no obvious way of folding that kind of information into the mass estimation. So, for example, you expect elliptical galaxies to maybe have a small, to maybe have larger halo mass at fixed stellar mass, for example. So such correlations are currently not being captured in current techniques using the fixed relation. So you would need machine learning to kind of feed that kind of information into the sausage machine, and hopefully a more accurate halo mass comes out on the other end.
I see. Okay, thank you. So I'm going to thank you again, and we're going to move on to our last speaker for the session, who is, this one is a recording, and we have Masoud Rafiei-Ravandi from Perimeter Institute speaking to us about probing the large-scale clustering of fast radio bursts with the first CHIME FRB catalog. And if any of his collaborators are present, or if he's present, we can head to them for questions. Okay.
Hi everyone. Thanks for having me today. My name is Masoud Rafiei-Ravandi, and I'm a PhD candidate at Perimeter Institute working with Kendrick Smith. I'm also a member of the CHIME Fast Radio Burst collaboration. In the next 15 minutes, I'm going to talk about fast radio bursts from a cosmological perspective. As you can see, CHIME is a big collaboration with teams across US and Canada. And this work has been a team effort, and I'm going to share with you some new results, which we recently published. As most of you know, I'm sure, fast radio bursts are single or repeating flashes of radio signal with unknown extragalactic origins. Like pulsars, FRB emission is dispersed as it passes through cold plasma along the line of sight. And the dispersion delay has a known frequency dependence. It's frequency to the -2. And the prefactor is what we call dm. It's a definition. And it's determined by how much electron is along the line of sight. So basically, it accounts for the contribution from Milky Way, intergalactic medium, and a host, which is completely unknown. Last time I checked, there were about 600 FRBs discovered with a bunch of repeaters and about 15 localized to their host galaxies. And these numbers just show how little we know about FRBs, and we need to use experiments to learn more about these sources because they can be used, perhaps they can be used as cosmological probes. So there are 2 main questions about FRBs. The first one I would say is what's the nature of FRBs? And the next one is, can they be utilized as cosmological probes? And I think in this session, we are trying to answer the second question, but this talk also sort of touches the first question as well. I should mention that once a dm is measured for an FRB, we have an upper bound on the redshift value of the FRB source because the host DM is completely unknown. Bright FRBs, according to the recent CHIME FRB results, are distributed randomly at a rate of about 1,000 per day over full sky. And out of about 600 FRBs, there are about 24 FRB sources that are repeating over long time intervals. They sporadically emit radio signal. Multiple radio bursts are emitted by the same source. And about 15 FRBs have been localized to their host galaxies, and mostly by ASCAP. And we know that most of the known FRB sources have been discovered by CHIME FRB, as you can see in the plot below. In the plot, I'm showing the new FRB catalog, like the first FRB catalog by CHIME FRB. And triangles show you the repeating sources in the sky. So CHIME was originally designed for 21 centimeter cosmology, but it turned out to be a fantastic FRB detector. Thanks to its large field of view and a huge bandwidth, it can detect a few FRBs per day. CHIME FRB is a state-of-the-art search engine, monitors the sky in real time. It has a millisecond time resolution and 16,000 frequency channels. And it has found about more than 1,000 FRBs to date. Our first catalog, containing 535 FRBs, has been published recently. And we also published 3 companion papers, as you may know, with the catalog. And the focus of this talk is on FRB galaxy cross correlations. And before I get to that, I would like to show you a timeline for CHIME FRB. Back in 2014, we had this small version of the full CHIME array, which we call it Pathfinder, and we were experimenting with the design of the instrument as well as the software, because as you know, CHIME is a software telescope, and we spent a few years just developing software for this experiment. Back in 2016, for example, I was mostly involved in removing RFI from the data from the Pathfinder telescope. And the software for CHIME has been written by a large team of researchers across Canada. In 2017, we got our first light, and I would like to remind everyone that at the time there were about 50 FRBs discovered, including 1 repeating source. And since then, CHIME has sort of revolutionized the field by discovering hundreds of FRBs and tens of repeating sources. The focus of this talk, as I mentioned earlier, is on FRB galaxy cross correlations, which we formalized back in 2020, and we forecasted in a paper with my supervisor and Kyo Masoud. We formalized and forecasted on the cross correlation, and the new data based on the new FRB catalog has been super useful for analyzing the actual cross correlation signal and finding and detecting the signal in the real data. And so I would like to, before I get started, I would like to give you a background what I mean by FRB galaxy cross correlations. For FRB surveys with high angular resolution, with typical angular resolution of about 1 arcsecond, we can associate FRBs directly to unique host galaxies so that we can measure the redshift. But CHIME angular resolution is a few arc minutes and it's not sufficient to make direct host associations. But it can still be useful for associating FRBs and galaxies statistically. So intuitively speaking, there will be an excess probability of finding FRBs in the vicinity of galaxies. And to be more exact, we compute the FRB galaxy cross power spectrum, the angular cross power spectrum, which is a Fourier space statistic as a function of the angular wave number or multiple. And in the next few slides, I'm going to describe what this statistic is, this CLFG, and F stands for FRB, G stands for galaxies. So angular cross power spectrum is a function of angular wave number. And you can think about angular wave number as 1 over the scale, the real scale on the sky. And any deviation from 0 quantifies the strength of FRB galaxy correlation. So intuitively, a harmonic space correlation at a wave number L corresponds to a real space angular correlation at separation angle pi over L. In the left panel on this slide, I'm showing you an example, a cross correlation between a galaxy population in a narrow redshift bin at centered at redshift of 0.4 with an FRB population with a median FRB redshift of 0.8 and an angular resolution of 1 arc minute. The function itself, the angular cross power spectrum, has two main terms. So one is the two halo term, which you can think about it as the correlation between FRBs and galaxies in two different halos. And the other term is the one halo term. And you can think about it as correlations between FRBs and galaxies inside the same dark matter halos, as shown on the right panel. And so the one halo term measures the correlation on a small angular scales, as you can see in the left panel in blue. And the two halo term measures the correlation between FRBs and galaxies in two different halos, as can be seen in green. And this correlation, or this two halo term correlation, arises because both FRBs and galaxies have to sort of correlate with the linear density field in our cosmology. And so our aim here is to measure this correlation function in the Fourier space and see how that correlation can be useful in understanding FRBs. So before I get started on the analysis part, I would like to summarize the results that we have obtained so far. These results are based on the CHIME FRB catalog 1. Just to summarize, we find a statistically significant cross correlation between our FRB sample and galaxies in redshift range 0.3, between redshift 0.3 and 0.5 in 3 galaxy surveys. The level of cross correlation is consistent with an order 1 fraction of our FRB sample being in the same dark matter halos as galaxies in these surveys. And in addition, we find a statistical evidence for a subpopulation of fast radio bursts with large host DMs. And by large, I mean host DMs of around 400 PCC. This is intriguing, given that we haven't seen such FRBs in direct host galaxy associations, which typically have, which typically exhibit DM hosts of around like between 50 to 200. We show that this large DM host contribution can be explained by a small population of FRBs near the centers of massive halos. Before I get into the analysis, I would like to show you the data that we worked with. On the FRB side, we have the FRB catalog. Our sample, as I said, it's the full sample is 535 FRBs, but we only count the unique events in our sample for this cross-correlation studies. So we have 489 unique events, and we exclude 43 low SNR bursts from repeating sources and 3 side lobe detections, just because side lobe detections tend to have less accurate localization. Using the real FRB sample, we also generate mock FRB catalogs and random FRB catalogs by randomizing right ascensions while keeping declinations fixed. And we use mock FRB catalogs for assigning error bars to the angular cross power spectrum. Randoms are used to make over density maps like the one that you see on the left panel in this slide. On the right panel on this slide, I'm showing you the FRB, the number of FRBs as a function of extragalactic DM, and each colored line shows you the fraction of those FRBs covered by each galaxy surveys that we used, and I'm showing you in the next slide. So these galaxy surveys that we use actually 5 galaxy surveys. They don't cover the entire sky. They have their own masks, for example, the star masks, like galactic plane masks, and so on. And so our FRB sample has partial overlap with these galaxy surveys, and these galaxy surveys cover a wide redshift range from redshift 0 to 1.4, and they are excellent candidates for doing cross correlation studies. Just because if you notice in the previous slide here, the extragalactic DM for FRB sample peaks at about 500. And if we assume that the host DM contribution is is negligible, then you would expect to see a cross correlation between our FRB sample and these galaxy surveys at somewhere around redshift 0.5. And so we cross-correlated these overdensity maps of galaxies with our FRB overdensity map, and we got some exciting results. Here, I'm briefly summarizing the results that we found. We find a statistically significant correlation between our FRB sample and galaxies in the redshift range 0.3 and 0.5 in 3 galaxy surveys. The first one is WISE cross-matched with Super Cosmos. The next one is DESI BGS, and the last one is DESI LRG. We don't find significant correlation with the other 2 galaxy catalogs. And I should mention here that we adopt a redshift cut for our galaxy catalogs. In other words, the angular cross-power spectrum, which I mentioned earlier as a function of angular wave number, is now a function of 2 variables. One is the angular wave number, the other one is redshift endpoint. So here, for example, in the top panel, I'm varying the minimum redshift cut for the WISE Supercosmos galaxy catalog. So my angular cross-power spectrum is now a function of angular wave number, as well as zoom in or minimum redshift cut. But in this plot, I'm just showing you a fixed zoom in, just because it's easier to look at the plot. By varying the redshift endpoint, we can basically constrain the correlation between our FRB sample and galaxies in the redshift space. On this plot at the top, I would like to go over the lines, what I mean by each data point here. So these bands in orange, these are the band powers. They are basically the CLFG, the angular cross-power spectrum, based on the cross correlation of our FRB over density map and the galaxy map with this redshift endpoint. The blue line is the galaxy autopower spectrum, and the dashed line in blue is the galaxy shot, the shot noise term. And we also have a fit to the angular cross-power spectrum to these band powers. And I will show you, I will describe what this fit means at a fixed characteristic scale in a moment. But just to
Masoud, a minute is left.
Okay, thank you. So just to emphasize that these band powers are all above 0, so we have a significant correlation with these galaxy samples. So if we use galaxy catalogs without redshift cuts, then we don't get a statistically significant detection. So in the next few slides, I will describe the steps for obtaining p-value. The first step is to fit the measured cross-power spectrum, these band powers, to a template, and we use a template which is an exponentially decaying template multiplied by a constant, and this was motivated by the CHIME FRB beam transfer function. In this running example, I'm cross-correlating DESI LRG galaxies with our FRB catalog, and the level of cross-correlation is significant. Now the question is, how do we go from the template to a cross-correlation SNR? And to do that, we go from the template to an optimal estimator for this template in alpha, which I don't go into details in this talk, and we call it alpha hat. And then we measure something which is a local significance of the cross correlation in sigmas, SNR as a function of L. And this big L is the characteristic scale of our template. So here local means for a fixed choice of L characteristic scale and the redshift endpoint, Zmax in our case, without incorporating Luckel sphere effects in a scale and redshift. In this example that I'm showing you, we see a significant correlation, SNR above 4 for scales that are about like 10 arc minutes, which is significant. But the question is, what is the global detection significance if we incorporate for Luckel sphere effects in angular scale and redshift endpoint? And to do that, we assign a global significance by maxing over the SNR local across 2 dimensions. Here we have angular scale L and also the redshift endpoint Zmax in the case of LRG. For the other 2 galaxy surveys, WISE and BGS, we vary zoom in. And after going through steps 1 to 3, we compute a p-value by asking the question of what is the fraction of max with SNR max greater than or equal to the SNR max of our data. And we get significant p-values, order of 10 to the -4. And that in the paper, we show that the level of cross correlation is consistent with an order 1 fraction of CHIME FRBs in the same dark matter halos as galaxies in those surveys. And here I'd like to emphasize that we are only detecting the 1 halo term. This slide, just to say a few words on the DM dependence of our results. If you just constrain your cross correlation analysis to the redshift range where you get the maximum signal, and then cross correlate with FRBs binned in DM, then you get this plot in this slide. And this is significant result because there seems to be a statistical evidence for a correlation between relatively high DM FRBs, which constitute a modest fraction of our entire FRB sample, and low Z galaxies. In particular, our results are consistent with an order of 1 fraction of our high DM FRBs being at redshift 0.4. And this is intriguing, as I said, given that most DM hosts from host associations have been shown to be between 50 to 200. And the question is whether this is consistent with direct host associations is the short answer is yes. And I won't take more time to go over details on this. Please let me know in the question period if you have more questions on this. And just to summarize, we predict that FRBs with extragalactic DMs greater than about 800 at redshift 0.4 will be found in direct association soon. However, future FRB surveys with higher sensitivity to fainter sources may show that FRBs with extragalactic DM greater than 800 will mostly come from redshift 0.8. So this DM dependence, we show that in the paper, the mechanism that can explain this DM dependence, and we show that propagation effects, which are associated with dispersion and scattering, are unlikely to explain the observed correlation. But a strong plasma and gravitational lensing can explain this, which in the paper we don't show actually the lensing calculations, but we postpone it to future work. And these are just possibilities that we would like to explore in future work. Thank you very much.
Thank you so much for that final talk of our session. I don't know if we have any of the paper collaborators present to answer questions. But I think there are no questions in the Q&A, and I don't see any in the chat. So perhaps this is a perfect chance to end exactly on time, maintain my reputation for keeping time, and defer, please, if you have any questions, follow up again in the Slack channel. For those of you who haven't figured out how to get on the Slack channel, Whaley Penn, please join the Slack channel. And thank you very much to all of our speakers and the attendees for the excellent conversation, dialogue, talks that we had in the session. It was really great. Thank you.